CIET NCERT presents audiobook Ganit Prakash, Part 2, Textbook of Mathematics for Grade 7.
Chapter number 3, page number 47. Finding common ground. On the right side of the page, we are provided with a QR code, scanning which we can reach out to the additional resources to this chapter. 3.1 The greatest of all. Samiksha is building her new house. The main room of the house is 12 feet by 16 feet. She feels that the room would look nice if the floor is covered with square tiles of the same size. She also wants to use as few tiles as possible and for the length of the tile to be a whole number of feet. What size tiles should she buy? Let us explore how to find the largest square tile that can be used. The breadth of the room is 12 feet and the length is 16 feet. We are provided with a picture here in which we find a rectangle with right angles marked at the corners, and length of the rectangle is 16 feet and breadth is 12 feet. For the tiles to fit the breadth of the room exactly, the side of the tile should be a factor of 12. Similarly, for the tiles to fit the length of the room exactly, the side should be a factor of 16. So, the side of the tile should be a factor of both 12 and 16. What are the common factors of 12 and 16? The factors of 12 are 1, 2, 3, 4, 6 and 12. The factors of 16 are 1, 2, 4, 8, 16. The common factors are 1, 2 and 4. So, the square tiles can have sides 1 feet, 2 feet and 4 feet. Among these, she should use the largest sized square tile. Can you explain why? Therefore, she needs tiles of size 4 feet. Page number 48. How many tiles of this size should she purchase? What if Samiksha did not insist on the length of the tile to be a whole number of feet and the length could be a fractional number of feet? Would the answer change? The highest common factor, HCF, of two or more numbers is the highest or greatest of their common factors. It is also known as the greatest common divisor, that is GCD. In the previous problem, 4 is the highest common factor of 12 and 16. An owl musket appears here to explain us that we can draw rough diagrams like the one given on the previous page to visualize the given scenario. It may help in understanding and solving. Lekna purchases rice from 2 farms and sells it in the market. She bought 84 kg of rice from one farm and 108 kg from the other farm. She wants the rice to be packed in bags. So, each bag has rice from only one farm and all bags have the same weight, that is a whole number of kg. If she wants to use as few bags as possible, what should the weight of each bag be? To divide 84 kg of rice into bags of equal weight, we need the factors of 84. Similarly, for 108, we need the factors of 108. Factors of 84 are 1, 2, 3, 4, 6, 7, 12, 14, 21, 28, 42 and 84. Factors of 108 are 1, 2, 3, 4, 6, 9, 12, 18, 27, 36, 54, and 108. Since Lekhna wants to use bags of the same weight for both farms, the weight of the bag should be a common factor. The common factors of 84 and 108 are 1, 2, 3, 4, 6, and 12. She can use any of these weights to pack rice from both farms in bags of equal weight. But she wants to minimize the number of bags. Which weight should she choose to minimize the number of bags? Do you remember the jump jackpot game from class 6? Find it in the chapter Prime Time. Grumpy places a treasure on a number and Jumpy chooses a jump size and tries to collect the treasure. In each case given here, the two numbers upon which treasures are kept are given. Find the longest jump size starting from 0 using which Jumpy can land on both the numbers having the treasure. A. 14 and 30. B. 7 and 11. C. 30 and 50. D. 28 and 42. Is the longest jump size for the numbers the same as their HCF? Explain why it is so. Page number 49. So far, we have been listing all the factors to find the HCF. This can become cumbersome for numbers with many factors, as you would have observed for the numbers 30 and 50 and 28 and 42. Sometimes we may also miss some factors which can lead to errors. Can this process be simplified? Can it be made more reliable? It turns out that using prime factorization can simplify the process. We will start by revisiting primes and prime factorization. Primes. Recall that a prime is a number greater than 1 that has only 1 and the number itself as its factors. Last year, we tried to find patterns amongst primes between 1 to 100. We also came across the sieve of Eratosthenes, a method to list all primes. Prime factorization. Any number can be written as a product of primes. Keep rewriting composite factors until only primes are left. Recall that we call this the prime factorization of a given number. For example, we can find the prime factorization of 90 as follows. 90 is equal to 3 into 3 into 2 into 5. The number 90 could also have been factorized as 3 into 30 or 2 into 45 or in a few other different ways. Will these all lead to the same prime factors? Remarkably, the resulting prime factors are always the same, with perhaps only a change in their order. For example, if we consider factorizing 3 into 30 further, we get 90 is equal to 3 into 30, that is equal to 3 into 2 into 15, that is equal to 3 into 2 into 3 into 5. And we have arrived at the same prime factors just in a different order. Note that the prime factorization of a prime number is the prime number itself. Procedure for prime factorization. Can you observe what is happening here? We have 105 when divided by 3 gives 35. When 5 divides 35, we get 7. Similarly, we have number 30. When 2 divides 30, we get 15. And when 3 divides 15, we get 5. This has been represented here with the help of circles. Page number 50. Each circled number is the product of the numbers that are to its left and below. For example, 30 is equal to 2 into 15, 15 is equal to 3 into 5. Each time a composite number is factorized so that at least one factor is prime. We stop when we reach a prime number. Can you write the prime factorization of 105 and 30 using these two figures? We collect the prime factors along the left and the one at the bottom. We then construct the prime factorization as given in the figure. While carrying out factorization, the circles are usually left out and the steps are carried out in this format. We have 105 divided by 3 gives 35. 35 again divided by 5 gives us 7. Likewise, 30 when divided by 2 gives 15, and when 3 divides 15, we get 5. On the right side, we can find that 105, which is written in circle, has factors 3 and 35. And when 5 divides 35, which is written in circle again, gives us 7 as its factor. Let us call this method the division method. Try finding the prime factorization of 1200 using the above method. If we had used the earlier method, our calculation would have been as follows. 1200 is equal to 40 into 30, that is equal to 5 into 8 into 5 into 6, that is equal to dash. Which calculation is easier to carry out? Factors of a number using prime factorization. From the prime factorization of a number, we can construct all its factors. This can be used to simplify the procedure for finding the HCF of two numbers. Consider the number 840 and its prime factorization. 2 into 2 into 2 into 3 into 5 into 7. Is 2 into 2 into 7 is equal to 28 a factor of 840? If yes, what should it be multiplied by to get 840? To answer these questions, we can reorder the prime factors of 840 as follows. Recall that reordering factors does not change the product. 840 is equal to 2 into 2 into 7 within brackets into 2 into 3 into 5 within brackets. 840 is equal to 28 into 30. Thus, 2 into 2 into 7 is equal to 28 is a factor of 840 and it should be multiplied by 30. 2 into 3 into 5 to get 840. Page number 51. Similarly, is 2 into 7 is equal to 14 a factor of 840? Why or why not? Is 2 into 2 into 2 a factor of 840? Why or why not? Is 3 into 3 into 3 a factor of 840? Why or why not? Can we use this idea to list down all the possible factors of a number using just its prime factors? Find the factors of 225 using prime factorization. Factorizing 225 to its primes, we get 225 is equal to 5 into 5 into 3 into 3. On the right side, we can see the factorization done as 225 when divided by 5 gives us 45. When 45 is divided by 5, we get 9. And when 9 is divided by 3, we get 3 as the factor. And when 3 again divides 3, we get 1. Factorizing 225 to its primes, we get 225 is equal to 5 into 5 into 3 into 3. We have learned that any subpart of this factorization gives us a factor. Let us systematically form these subparts. Prime factors 3 and 5. Combination of two prime factors 3 into 3 is equal to 9. 5 into 5 is equal to 25. 3 into 5 is equal to 15. Combination of 3 prime factors 3 into 3 into 5 is equal to 45. 3 into 5 into 5 is equal to 75. Combination of 4 prime factors 3 into 3 into 5 into 5 is equal to 225. Adding 1 to this list of factors, we see that the factors of 225 are 1, 3, 5, 9, 15, 25, 45, 75, 225. Check that all the factors of 225 occur in this list. Figure it out. List all the factors of the following numbers: A 90, B 105, C 132, D 360. This number has 24 factors. E 840. This number has 32 factors. After observing a few prime factorizations, Anshu claims the larger a number is, the longer its prime factorization will be. What do you think of Anshu's claim? We can find that it is not true. For example, look at the prime factorization of 96 and 121. 96 can be factorized as 2 into 2 into 2 into 2 into 2 into 3. And 121 is equal to 11 into 11. Page number 52. An owl musket appears here to explain that in mathematics, statements or claims made without proof or verification are called conjectures. Anshu's claim is a conjecture. We disproved this conjecture by finding a counterexample, that is, an example where the conjecture is false. Finding the HCF of numbers using prime factorization. We now learn how to make use of the observations made so far to find common factors and the highest common factor HCF. Example 1. Find the common factors and the HCF of 45 and 75. Calculate the prime factorization for both numbers. 45 is equal to 3 into 3 into 5. 75 is equal to 3 into 5 into 5. We have observed factors of 45 are subparts of factors occurring in 3 into 3 into 5, and factors of 75 are subparts of factors occurring in 3 into 5 into 5. So, the common factors should be subparts of both the factorizations. Can you write them down? An owl musket appears here again to explain us while exploring or solving problems. You might also get some conjectures. You can try to reason and verify these and also share with the class. 3 into 3 into 5, 3 into 5 into 5. 3 is a common factor in these. Likewise, 3 into 3 into 5, 3 into 5 into 5, 5 is a common factor in these both. So, 3 into 3 into 5 and in 3 into 5 into 5, 3 into 5 are the common factors. 3, 5, 3 into 5 is equal to 15 are subparts of both, and hence they are the common factors along with 1. The highest among them is 15. So, their HCF is equal to 15. Example 2. Find the common factors and the HCF of 112 and 84. Calculating prime factorizations, we get 112 is equal to 2 into 2 into 2 into 2 into 7, and 84 is equal to 2 into 2 into 3 into 7. Page number 53. Finding the common subparts, we get 2 into 2 into 2 into 2 into 7, 2 into 2 into 3 into 7, 2 is common here. Likewise, 2 into 2 into 2 into 2 into 7 and 2 into 2 into 3 into 7, we find 7 is common in these two. So, 7 is a common factor. Next, 2 into 2 into 2 into 2 into 7, 2 into 2 into 3 into 7, we find 2 into 2 is a common factor in both. 2 into 2 into 2 into 2 into 7 and 2 into 2 into 3 into 7. Here we find 2 and 2 7 is a common factor in both. Likewise, 2 into 2 into 2 into 2 into 7 and 2 into 2 into 3 into 7, we find that 2 into 2 into 7 is also common in both these numbers. The highest among the common factors, HCF, is 2 into 2 into 7, that is equal to 28. Example 3. Find the common factors and the HCF of 96 and 275. We have 96 is equal to 2 into 2 into 2 into 2 into 2 into 3, and 275 is equal to 5 into 5 into 11. There is no subpart that is common amongst these two factorizations. So, 1 is the only common factor. It is also their HCF. Figure it out. Find the common factors and the HCF of the following numbers. A. 50, 60. B. 140, 275. C. 77, 725. D. 370, 592. E. 81, 243. How do we directly find the HCF without listing all the factors? Example 4. Find the HCF of 30 and 72. 30 is equal to 2 into 3 into 5. 72 is equal to 2 into 2 into 2 into 3 into 3. We need the largest common subpart to find the HCF. Clearly, it will contain all those primes that occur in both the factorizations, 2 and 3 in this case. How many 2's will it contain? Page number 54. The prime factorization of 30 has only one 2. So, the largest common subpart should contain only one 2. How many 3's will it contain? The prime factorization of 30 has only one 3. So, the largest common subpart should contain only 3. This has been carried out here as 30 is equal to 2 into 3 into 5, 72 is equal to 2 into 2 into 2 into 3 into 3. So HCF is equal to 2 into 3, that is equal to 6. Thus, to find the HCF, we identify the common primes and find the minimum number of times each of them appear in the factorizations of the given numbers. Example 5. Find the HCF of 225 and 750. 225 is equal to 3 into 3 into 5 into 5. 750 is equal to 2 into 3 into 5 into 5 into 5. Common primes 3 and 5. Let us find the largest common subpart. How many 3's will it contain? 750 contains only one 3, which is the minimum number of 3 across both numbers. So, the largest common subpart should contain only one 3. How many 5's will it contain? 225 contains the minimum number of 5's, which occurs 2 times. So, the largest common subpart should contain 2 5's, that is 5 into 5. We are explained the process here. 225 is equal to 3 into 3 into 5 into 5, and 750 is equal to 2 into 3 into 5 into 5 into 5. We find that 3 into 5 into 5 are common in both the numbers. So, HCF is equal to 3 into 5 into 5, that is equal to 75. To find the HCF of more than two numbers, a similar method of finding the largest common subpart of the common primes can be followed. Figure it out. Question number 1. Find the HCF of the following numbers: A. 24, 180. B. 42, 75, 24. C. 240, 378. D. 400, 2500. E. 300, 800. Question number 2. Consider the numbers 72 and 144. Suppose they are factorized into composite numbers as 72 is equal to 6 into 12 and 144 is equal to 8 into 18. Observing this, can one say that these two numbers have no common factor other than 1? Why not? Page number 55. 3.2 Least but not last. Anshu and Guna make torans out of strips of cloth. Multiple strips are placed one next to another to make a toran. Anshu uses strips of length 6 cm and Guna uses strips of 8 cm length. If both have to make torans of the same length, what is the smallest possible length that torans could be? What is the length of the shortest toran that they can both make? Anshu uses cloth strips of 6 cm each. Any toran he makes will be a multiple of 6. So, the length of the toran could be 6, 12, 18, 24, 30, 36, 42, 48, 54 centimeters and so on. Similarly, any toran Guna makes should be a multiple of 8. So, the length of the toran he makes could be 8, 16, 24, 32, 40, 48, 56, 64, 72 centimeters and so on. Here in the picture, we can find Anshu and Guna. They are making torans with the pieces of cloth. From this, we can observe that if both have to make torans of the same length, the length of the toran should be a common multiple of 6 and 8. From the two lists, we can find that 24 and 48 are two of the common multiples of 6 and 8. So, 24 centimeters and 48 centimeters are lengths of toran that Anshu and Guna can both stitch. 24 is the smallest among them. So, 24 centimeters is the length of the shortest toran that both can stitch. 24 is the lowest number among all the common multiples of 6 and 8. What about the largest common multiple? Does such a number exist? A sweet shop gives out free gajak to school children on Mondays. Today is a Monday and Kabamai enjoyed eating the gajak. But she visits the sweet shop once every 10 days. When is the next time she would be able to get free gajak from sweet shop? Answer in number of days. We can find a picture of a sweet box in which gajak is placed. Gajak is a sweet made from sesame seeds, jaggery and ghee. An owl musket appears again here to explain us, as we have seen before, imagining or visualizing the scenario helped us to find that it can be solved using multiples of the strip's lengths. Since the shop gives free sweets every Monday, it will give free sweets again after 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, 77 and so on days. These are multiples of 7. Page number 56. Kabamai will arrive at the sweet shop again after 10, 20, 30, 40, 50, 60, 70 and so on days. These are multiples of 10. When will Kabamai eat free sweets again? It will happen on days common to the sequences of multiples given here. It can be seen that this will first happen after 70 days. Notice that here too 70 is the lowest among all the common multiples of 7 and 10. For both these problems, the solution was the lowest common multiple. The lowest common multiple, LCM of two or more given numbers, is the lowest or smallest or least of their common multiples. Do you remember the Idli Vada game from grade 6? Locate chapter Prime Time. Two numbers are chosen and whenever players come to their multiples, Idli or Vada should be called out depending on whose multiple the number is. If the number happens to be a common multiple, then Idli Vada should be called out. In each problem given here, the two numbers corresponding to Idli and Vada are mentioned. Find the first number for which Idli Vada will be called out. A. 4 and 6. B. 7 and 11. C. 14 and 30. D. 15 and 55. Is the answer always the LCM of the two numbers? explain. As in the case of the HCF, the process of finding the LCM by listing down the multiples may get tedious for larger numbers, as you would have observed for questions C and D given here. Prime factorizations can simplify the process of finding the LCM as well. How do we find the LCM of two numbers using their prime factors? Finding LCM through prime factorization. We have learned that every factor of a number is formed by taking a subpart of its prime factorization. We use this fact to come up with a method to find the HCF of two numbers. In a similar manner, we can come up with a method to find the LCM. We begin by comparing the prime factorizations of a number and a multiple of that number. For example, let us take 36 and its multiple 648. That is equal to 36 into 18. Page number 57. We get 36 is equal to 2 into 2 into 3 into 3. 648 is equal to 36 into 18, that is equal to 2 into 2 into 3 into 3 within brackets into 2 into 3 into 3 within brackets. What do you observe? We can find that the prime factors of the multiple contain the prime factors of the number along with some more prime factors. Will this happen with every multiple? Can this be used to find the LCM? Example 6. Find the LCM of 14 and 35. We get 14 is equal to 2 into 7. 35 is equal to 5 into 7. Common multiples should contain each prime factor as a subpart. 2 into 7 as a subpart and 5 into 7 as a subpart. For example, 2 into 7 into 5 into 7 into 3 is a common multiple of 14 and 35. 2 into 2 into 5 into 7 into 7 into 11 is another common multiple. Is 2 into 3 into 5 into 7 also a common multiple? What is the lowest among all the common multiples of 14 and 35? It is 2 into 5 into 7 is equal to 70, because 2 into 5 into 7 contains 14 is equal to 2 into 7 as well as 35 is equal to 5 into 7, and removing any number from 2 into 5 into 7 will get a number that is not a common multiple of 14 and 35. Example 7. Find the LCM of 96 and 360. We have 96 is equal to 2 into 2 into 2 into 2 into 2 into 3. 360 is equal to 2 into 2 into 2 into 3 into 3 into 5. Every common multiple should contain the prime factors of both 96 and 360. For the LCM, we will need the smallest such number. Let us build the LCM looking at each prime factor. The prime factors appearing in both the numbers are 2, 3 and 5. Now we shall find out how many occurrences there are for each prime factor. How many 2's should the LCM contain? The factorization of 96 contains 2 into 2 into 2 into 2 into 2, 5 occurrences of 2's. And the factorization of 360 contains 2 into 2 into 2, 3 occurrences of 2's. Choosing 5 occurrences of 2's as part of LCM will contain both these subparts. Page number 58. Choosing more than 5 occurrences of 2's will give a common multiple, but it will not be the lowest. Are you able to find why? How many 3's should the LCM contain? The factorization of 96 contains 3. One occurrence of 3 and the factorization of 360 contains 3 into 3, 2 occurrences of 3's. Choosing 2 occurrences of 3's as part of LCM will contain both these subparts. How many 5's should the LCM contain? The factorization of 96 doesn't have any 5's, and the factorization of 360 has one occurrence of 5. So, we choose one occurrence of 5 to be a part of the LCM. Thus, the LCM of 96 and 360 will be 2 into 2 into 2 into 2 into 2 into 3 into 3 into 5, that is equal to 1440. To build the LCM of two numbers, we can identify all the prime factors and find the maximum number of times each of them occur in either of the factorizations. This process can be extended to find the LCM of two or more numbers. Figure it out. Find the LCM of the following numbers: A. 30, 72. B. 36, 54. C. 105, 195, 65. D. 222, 370. 3.3 Patterns, Properties and a pretty procedure. The HCF of 6 and 18 is 6, which is one of the two given numbers. Find more such number pairs where the HCF is one of the two numbers. How can we describe such pairs of numbers? We can find that it happens when one number is a factor of the other. This also means the other number will be a multiple of the first number. Such a statement describing a pattern or a property that holds in all possible cases is called the general statement. This process is called generalization. Such a generalization can also be described using algebra. Let us find out how. Here there is a beautiful picture in which we find number 18 and 6. Number 18 says, "Be my factor, I will be your multiple." They are playing with a ball. Page number 59. If n is a number, then any multiple of n can be written as a positive integer multiplied by n. For example, if we take n and 5n, short for 5 into n, then 5n is a multiple of n and n is a factor of 5n. The HCF of n and 5n is equal to n. For number pairs satisfying this property, that is, one of the numbers is the HCF. A. If m is a number, what could be the other number? B. If 7k is a number, what could be the other number? Figure it out. Question number 1. Make a general statement about the HCF for the following pairs of numbers. You could consider examples before coming up with general statements. Look for possible explanations of why they hold. A. 2 consecutive even numbers. B. 2 consecutive odd numbers. C. 2 even numbers. D. 2 consecutive numbers. E. 2 co-prime numbers. Share your observations with the class. Question number 2. The LCM of 3 and 24 is 24. It is one of the two given numbers. A. Find more such number pairs where the LCM is one of the two numbers. B. Make a general statement about such numbers. Describe such number pairs using algebra. Question number 3. Make a general statement about the LCM for the following pairs of numbers. You could consider examples before coming up with these general statements. Look for possible explanations of why they hold. A. 2 multiples of 3. B. 2 consecutive even numbers. C. 2 consecutive numbers. D. 2 co-prime numbers. What happens to the HCF of two numbers if both numbers are doubled? Take some pairs of numbers and explore. Are you able to find why the HCF will also double? Page number 60. If both numbers are doubled, then both numbers get an extra factor of 2 in their prime factors. This 2 will be included as a factor in the largest common subpart, and so the HCF will double. For example, consider the numbers 270 and 50. 270 is equal to 2 into 3 into 3 into 3 into 5. 50 is equal to 2 into 5 into 5. So HCF is equal to 2 into 5, that is equal to 10. Let us double these numbers to get 540 and 100. 540 is equal to 2 into 2 into 3 into 3 into 3 into 5. 100 is equal to 2 into 2 into 5 into 5. So HCF is equal to 2 into 2 into 5, that is equal to 20. Consider the following two multiples of 14. 14 into 6, 14 into 9. What is their HCF? Clearly, 14 is a common factor. Is it also the highest common factor? To find it, let us calculate the prime factorizations. 14 into 6 is equal to 2 into 7 into 2 into 3. 14 into 9 is equal to 2 into 7 into 3 into 3. HCF is equal to 14 into 3, that is equal to 42. Here are some more numbers where both numbers are multiples of the same number. Find their HCF. A. 18 into 10, 18 into 15. B. 10 into 38, 10 into 21. C. 5 into 13, 5 into 20. D. 12 into 16, 12 into 20. In which of these cases is the HCF the same as the common multiplier, like problem B, where the HCF is 10? Explore a few more examples of this type to understand when this happens. Efficient procedures for HCF and LCM. See the procedure on the right. Can you explain how it has been carried out? We have numbers 84 and 180 written together. We find its factors by dividing these numbers by 2. We get 42 on dividing 84 by 2, and we get 90 on dividing 180 by 2. Again, we divide 42 and 90 by 2 to get 21 and 45. Now we find that 3 can divide both the numbers 21 and 45. So 3 sevens are 21 and 3 15s are 45. Page number 61. This is similar to the procedure for prime factorization. At each step, the two numbers are divided by a common prime factor and the two quotients are written down in the next row. This continues till we get two numbers that do not have any common prime factors. How do we use this to find the HCF of 84 and 180? Explore. Hint: observe that 84 is equal to 2 into 2 into 3 into 7 and 180 is equal to 2 into 2 into 3 into 15. Similar to prime factorization. Find the HCF in the following cases. We have 300 and 150. When 2 divides these numbers, we get 150 and 75. Next, we divide 150 and 75 by 5 to get 30, 15. Again 5 divides 30 and 15 to get 6 and 3. Now 3 divides 6 and 3 to get 2 and 1. So the HCF is 2 into 5 into 5 into 3, which has been shown in the picture. Next we have 630 and 770. When 2 divides 630 and 770, we get 315 and 385 respectively. When 5 divides these two numbers, 5 divides 315 to give 63 and 5 divides 385 to give 77. Now 7 divides 63 to give 9 and 7 divides 77 to give 11. So HCF is 2 into 5 into 7, which has been represented in the figure. This procedure not only gives the highest common factor but can also be used to find the LCM. Can you see how? We have 300 and 150. We divided by 2 to get 150 and 75. Again 5 divided 150 and 75 to give 30 and 15. Next 5 divided 30 to give 6 and 5 divided 15 to give 3. Next 3 divided 6 to give 2 and 3 divided 3 to give 1. So LCM is 2 into 5 into 5 into 3 into 2 into 1. And in the next case we have 630 and 770 divided by 2, which gives 315 and 385. 5 divides 315 and 385 to give 63 and 77. 7 divides 63 and 77 to give 9 and 11. Now 3 divides 9 to give 3 and 11 is written as it is because it is not divided by 3. So LCM is 2 into 5 into 7 into 3 into 3 into 11. Why are these the LCMs? Hint: will the product of the factors marked as the LCM of 300 and 150 contain the prime factorization of both 300 and 150? Is this the smallest such number? Guna says, I found a better way to factorize to find HCF and LCM. This is faster than what we taught in class. For the numbers 300 and 150, I can first directly divide both numbers by 50. The HCF will be 50 into 3. We can find 300 and 150 is divided by 50 here to get 6 and 3 respectively. Now 3 divides both 6 and 3 to give 2 and 1. We also find a beautiful picture of Guna besides this problem. Page number 62. The LCM will be 50 into 3 into 2 into 1. Anshu also tried to remove the bigger common factors. We find the picture of Anshu on the right side of the page. For 630 and 770, I will divide both numbers by 10 first. Now, I can divide them by 7. 630 and 770 are divided by 10 to give 63 and 77. Again, 7 divides 63 and 77 to give 9 and 11 respectively. The HCF will be 10 into 7 is equal to 70. The LCM will be 10 into 7 into 9 into 11, that is equal to 6930. Can you find why this works? We need not restrict ourselves to dividing only prime factor at a time. Both numbers can be divided by whatever common factor we are able to identify. You can try this method for these pair of numbers: A 90 and 150, B 84 and 132. Property involving both the HCF and the LCM. Which is greater, the LCM of two numbers or their product? You could analyze the above statement using examples. Then try to reason or prove why the LCM is never greater than the product of the numbers. Hint: is the product also a common multiple of the two numbers? There is an interesting relation between the product of two numbers and their HCF and LCM. Consider the numbers 105 and 95. Find their LCM, factorizing them into their primes. 105 is equal to 3 into 5 into 7. 95 is equal to 5 into 19. LCM is equal to 3 into 5 into 7 into 19. Let us consider the product in the factorized form. 105 into 95 is equal to 3 into 5 into 5 into 7 into 19. Is the LCM a factor of the product? If yes, what should it be multiplied with to get the product? It can be observed that 105 into 95 is equal to LCM into 5. Explore whether the LCM is a factor of the product in the following cases. If yes, identify the number that the LCM should be multiplied by to get the product. Do you find any pattern? Use these numbers: A 45, 105, B 275, 352, C 222, 370. Page number 63. Do you find that in each case, the number by which the LCM is multiplied to get the product is actually the HCF? Thus, our observations seem to suggest the following: HCF into LCM is equal to product of the two numbers. Why does this happen? Can you give an explanation or proof? Hint provided is: consider the prime factorization of the given numbers. Among their prime factors, some are common to both factorizations, and the rest occur in only one of them. Between the HCF and the LCM, see how the common and non-common prime factors get distributed. In the product, observe how these two kinds of prime factors occur. Compare them. Explore whether this property holds when three numbers are considered. Figure it out. Question number 1. In the two rows given here, colors repeat. When will the blue stars meet next? We have picture of stars here in the given pattern: yellow, green, orange, blue, pink, grey, yellow, green, orange, blue, pink, grey, and so on. In the next row, we have green, orange, yellow, blue, green, orange, yellow, blue, green, orange, blue, orange, yellow, blue, and so on. 2a is 5 into 7 into 11 into 11 a multiple of 5 into 7 into 7 into 11 into 2? B is 5 into 7 into 11 into 11 a factor of 5 into 7 into 7 into 11 into 2? Question number 3. Find the HCF and LCM of the following. State your answers in the form of prime factorizations. A. 3 into 3 into 5 into 7 into 7 and 12 into 7 into 11. B. 45 and 36. Question number 4. Find two numbers whose HCF is 1 and LCM is 66. Question number 5. A cowherd took all his cows to graze in the fields. The cows came to a crossing with 3 gates. An equal number of cows passed through each gate. Later, at another crossing with 5 gates again, an equal number of cows passed through each gate. The same happened at the third crossing with 7 gates. If the cowherd had less than 200 cows, how many cows did he have? Based on the folklore mathematics from Karnataka. Page number 64. Question number 6. The length, width, and height of a box are 12 centimeters, 18 centimeters, and 36 centimeters respectively. Which of the following sized cubes can be placed in this box without leaving gaps? A. 9 centimeters, B. 6 centimeters, C. 4 centimeters, D. 3 centimeters, E. 2 centimeters. Question number 7. Among the numbers given here, which is the largest number that perfectly divides both 306 and 36? A. 36, B. 612, C. 18, D. 3, E. 2, F. 360. Question number 8. Find the smallest number that is divisible by 3, 4, 5 and 7 but leaves a remainder of 10 when divided by 11. Question number 9. Children are playing fire in the mountain. When the number 6 was called out, no one got out. When the number 9 was called out, no one got out. But when the number 10 was called out, some people got out. How many children could have been playing initially? A. 72, B. 90, C. 45, D. 3, E. 36, F. None of these. Question number 10. Tick the correct statements. The LCM of two different prime numbers m and n in brackets can be A. Less than both numbers, B. In between the two numbers, C. Greater than both numbers, D. Less than m into n, E. greater than m into n? Question number 11. A dog is chasing a rabbit that has a head start of 150 feet. It jumps 9 feet every time the rabbit jumps 7 feet. In how many leaps does the dog catch up with the rabbit? Question number 12. What is the smallest number that is a multiple of 1, 2, 3, 4, 5, 6, 8, 9 and 10? Do you remember the answer from grade 6, chapter 5? Question number 13. Here is a problem posed by the ancient Indian mathematician Mahaviracharya, 850 CE. Add together 8 upon 15, 1 upon 20, 7 upon 36, 11 upon 63 and 1 upon 21. What do you get? How can we find this sum efficiently? Page number 65. Summary. First point. Last year we looked at common multiples and common factors and were also introduced to the amazing world of primes. Second point. In this chapter we learned a method to find the prime factorization of a number. Third, finding all the factors of a number from its prime factorization is easy but quite tedious. We have to list every possible subpart. Fourth point, the highest common factor HCF is the highest among all the common factors of a group of numbers. Fifth point, every common factor is contained in the prime factorization of the number. Sixth point, to find the HCF we include the minimum number of occurrences of each prime across the prime factorization of all the numbers. Seventh point, the lowest common multiple LCM is the lowest among all the common multiples of a group of numbers. Eighth point, every common multiple contains the prime factorization of the numbers. Ninth point, to find the LCM, we include the highest number of occurrences of each prime across the prime factorizations of all the numbers. 10th point, we explored more about HCF and LCM. We discovered related properties and patterns when numbers are consecutive, even, co-prime, etc. 11th point, we learned a procedure to get both the HCF and the LCM at the same time. We also saw how to make this even quicker. 12th and last point, we learned some terms that are used when discussing mathematics such as conjecture and generalization. We also find a picture of a boy here saying that if I start writing this number, how long could it take me? The largest prime found so far has 4, 10, 24, 320 digits. It was discovered on October 12, 2024. Page number 66. Puzzle time. Mystery colors. You might have noticed and wondered about these different circle designs around the page numbers on each page. The picture given here explains all the designs for the numbers from 1 to 100. Try to decode the color scheme for each number. There are several interesting patterns here. Share your observations with your classmates. Extending this scheme, color the page numbers from 101 to 110. We are provided with a picture of numbers in circles written from 1 to 100. They have the color patterns as given on each page of this textbook. We also find below picture of kids wondering at this puzzle. Chapter 3 ends here.
Ganit Prakash, Part 2. You were just listening to this audiobook, Textbook of Mathematics for Grade 7. Narration, Swarnlata Sharma. Sound recordist, Prasoon Kumar. Assistance in production, Amarjeet Sarkar. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.